Hi everyone, on to 5.1 and 5.2. So this continues our march toward the second pillar of Calc 1, which is integration. And we saw that beginning in the last chapter with antiderivatives. As I said at the beginning of the course, there's kind of these two pillars of Calc 1. And one of those is the derivative. And we talked largely about the derivative the first half of the semester. And the derivative's job, in part, is to tell us how quickly some quantity is changing with respect to maybe a time, for example, or another quantity. So if you want to know, oh, this particle is moving in this direction, you might want to know how fast it's moving in that direction. Or if a ladder is sliding down a wall and you want to know how fast that bottom of the ladder is moving when the top of the ladder is some distance above the ground, you could figure that out through the derivative. So when things are changing, when you want to know how those things are changing, the derivative is a good approach. Antiderivatives, integration, what we're getting into now is more of an accumulation type of quantity. So if you're looking at, let's say, some container that is emptying. So the derivative might tell us how quickly the height of the liquid in that container is changing. The antiderivative or the integral can tell us how much liquid has accumulated on the ground or wherever it's draining into. So derivative, kind of how quickly something is changing. Integration, how much of that thing has accumulated. So what we're going to do first is look at 5.1. So imagine we have the velocity function of a particle over some journey, but we want to know the distance that the particle traveled during that journey. Okay, so imagine, for example, one here, we have this particle moving according to its velocity function, which is just this constant. So it's traveling at a constant velocity. This particle's on cruise control. So it's just going 7, and I guess I'm going to think of this as like meters per second. And that's for x in 0 to 10. I guess I'm talking about hours, and v is in miles per hour. So let's talk about miles in miles per hour instead of meters and seconds. So it says find the distance traveled during this journey. So what I'll do, I'll use this hint. It says graph the function and look at the area under the curve. So what I'll do is I'll go ahead and graph v of x. So this will be my axis for v. This will be my axis for x. So I have v of x is this constant function going all the way out to 10. Right? So there's v of x. And we want to know, if this is the velocity function, we want to know how far this particle traveled. So just a bit of a sidebar. For rectangles, we know that the area interior to a rectangle would be the length times the width of that rectangle. So just as a matter of curiosity, what would the area under this curve represent? So if I now focus on the area under this curve, which happens to be a rectangle, what would the area under that curve represent? Is it distance, like we're wondering? Is it a number of dolphins? Is it an amount of money? How can we figure that out? So one way to do this is to multiply the units. So V would have units of miles per hour, and then X would have units of hours. So over here, this vertical would have units of miles per hour. And if I multiply by the length of this side of the rectangle, that would have units of hours. When that multiplication takes place, we can cross out hours, and this would be equal to just miles, actually. So the area under this curve here, it actually represents miles in terms of units. So the area under this curve actually would literally be the distance that this particle traveled. So what I'll do is the distance will be equal to this length, which is 7 miles per hour. And then I would multiply by this length of the rectangle here, which is 10 hours. When that multiplication occurs, these units cancel just the same as they did above. And we get 70 miles. Okay. So that would be the area under the curve in this case, and that would be the answer to this question. All right, let's try another one. Example 2. So again, I'm going to think of this as my kind of v of x axis, and this is my x-axis. Let's see what it says. A particle is moving according to its velocity function. So again, it's v that we're given. And this time it's x plus 2, so it's a non-constant velocity in this case, for x in 0 to 10, where x again is in hours and v again is in miles per hour. It says find the distance traveled during this journey. So I'll start in a similar way. So let's plot this x plus 2. So we'd have a v-intercept of 2, and then I would go up 1 over 1. And that just so happens to land at 10, the end of our interval. So this straight line here would be our velocity function. So just as before, we're wanting to know the distance that this particle traveled. It says find the distance traveled during this journey. Hint, graph the function and look at the area under the curve. So because this is another velocity function, and its units are miles per hour, and because this is another time variable, and its units are hours, when we take the area, so when we look at the area under this curve, all this stuff here, the units of that area will come from taking miles per hour times hours, and that'll again leave us with miles. So again, this area under the curve is the distance. Okay, so if we can find this area exactly, then we know the answer to this question exactly. So it looks like to me we have essentially a triangle and a rectangle. All right, you see what I mean by there? There's this rectangle down here. There's this triangle up here. So in other words, the area of the triangle plus the area of the rectangle will equal the distance here. Okay. So in other words, to find an area of a triangle, I need 1/2 the base times the height. For the area of the rectangle, I'll just have length times width, or base times height. And this will equal the distance. So starting with the triangle, it looks like we have a base 10 and a height going from 2 to 12. So we have a base 10 and a height of 10. So I'll have 1/2 10 times 10, right? 10 for the base. And going from 2 to 12 means we have a 10 for the height, just for the triangle, right? I'm just talking about the triangle. And then I'll need to add to that the area of this rectangle here. So that'll be 10 times 2. This will equal the distance. So we have 50 plus 20 equals the distance. So this thing went 70 miles. Not all particles go 70 miles, but these two happen to. All right, so on to example 3. It says a particle is moving according to its velocity function. So we still have a velocity function here, and that it looks like will be in miles per hour. I'll write that down. And then we have that it's x squared this time, this velocity function, and we're going just from 0 to 3. So I've done my scale this way this time, where x is in hours, so maybe I'll say that over here, x hours. What else? It says graph the function and look at the area under the curve. So for the graph, 0, 0 would be on the graph. 1, 1 would be on the graph. 2, 4 would be on there because we have x squared. 3 squared would be 9. And then I'll draw this curve the best I can. Okay, so what we're tasked to do with now is to find the exact area under this curve. However, there's a difference. Right, there is a difference between this one and our previous 2 examples. So the main difference is if you think about the area under this curve, this is a curving curve. So this is not a triangle here, right? It's similar to a triangle, but it's not exactly a triangle. So if we were looking for the exact area, we would not be able to do it with that same approach of rectangles and triangles only. So in general, we will need calculus to find this exact area. So for that reason, we will need to estimate. So we're going to use some rectangles. I'll use 3 rectangles, and I'll estimate using those 3 rectangles. What it's saying to do is to first estimate with the left endpoints. So I'll do these left endpoints in light blue, and then I'll try to do these right endpoints in darker blue. Hopefully it'll come up on the screen for you guys. And then we will take the average of those 2. So that's how we'll do our estimate. So it's going to be what we'll see as an underestimate. So this will be an underestimate. This will be an overestimate. And then to make a better estimate, we'll take the average of those 2. So let me show you how the picture goes. So if I have 3 rectangles, let's just imagine I wanted to use 3. So for left endpoints, what we do is in this first interval, right, here's 1, 2, 3. So I'll use those 3 rectangles. So for left endpoints, I start at the left endpoint of my interval, and then I go up until I hit the function, or down until I hit the function, depending on the case. In this interesting case, the function is already right at my pen. So what I do is I have a rectangle of 0 height, and then I'll just draw over. So it's really a degenerate rectangle. For the second one, here's my second interval. Here's the left endpoint of it. So I go up until I hit the function, and then I go to the right to the end of the interval. Here's my second rectangle here. That's really my first rectangle technically, because this is really just a line. I'm not going to produce any area out of that. So here's my third interval. Here's my left endpoint of it. I go up until I hit the function, and then I make this rectangle to the right. So I can estimate the the underestimate will come from the area of these rectangles, right? So I have 1, 2, 3, technically, rectangles. So the area, well, for the first one, to get the height of that rectangle, I was plugging in 0 into the function, right? So the height of that first rectangle, so maybe I'll call it the first rectangle, the height would be f of 0. The length of that rectangle would be the length of our interval, which will be 1. So times 1. That's the first rectangle there. Then I would need to add the second rectangle. The height of it comes from taking f of 1, right? That would be the height of this rectangle. And then its width, again, is 1. And then plus this third one, we have a height of f of 2, right? Because that's the number that is evaluated to create the height of this rectangle. And then again, it's a width of 1. So simplifying this, f of 0, and by f, I really should have been writing v. I apologize for that. So it should have been v's. Because our function really is v, not f. So v of 0 is 0 times 1 plus v of 1 is 1 times 1 plus v of 2 is 4 times 1. So our underestimate, we have 0 plus 1 plus 4, so we have 5. And that would be miles, since those are areas, again, under a velocity curve. So that's our underestimate. For the overestimate, those are right endpoints. So what we do for that is, here's my same interval. I then go to the right of that interval. I go up until I hit the function, and then I make a rectangle to the left. So here's my second interval. I go to the right endpoint, I go up, and then I make my rectangle to the left. And then here's my third interval. I go to the right endpoint of it, and then I go up until I hit the function, and then go left until I hit the other end of the interval. So those darker rectangles, so all of this stuff, and it does encroach all the way down, all of this stuff will be my overestimate. So its area. So the first one would be, so this height of this first rectangle would come from taking v of 1 times the width of the rectangle. Right, so here's v of 1, the height of the rectangle, and then 1 is the width. So plus rectangle 2, its height comes from taking v of 2, and its width again is 1. And then finally this third, so we add this third rectangle here, so its height is coming from evaluating the function at 3. So I'll have v of 3 as its height, and then times 1 as the width again. So v of 1 is 1, so I'll have 1 times 1, plus v of 2 is 4, so I'll have 4 times 1, plus v of 3 is 9, so 9 times 1. So my overestimate would be 1 plus 4, 5 plus 9 is 14 miles. And then to make my best guess possible, and really it's still not exact, but it's a better estimate to say, so my estimate would be 5 miles plus 14 miles divided by 2. So 19 halves miles, roughly. Okay, so thinking about our approach, the question at the bottom of the page says, how could we improve the above estimates? So there's at least one way. What if we had taken more rectangles? Like I just arbitrarily decided to do 3. We were going from 0 to 3, so that made sense. But what if I took 6? Or what if I took 6 million? Or what if I took 6 trillion rectangles, right? That would be a lot more work, but our estimate would actually get better and better. So how can we improve? Or maybe I'll say use more rectangles. So if we were to use more rectangles, the widths of those, or the lengths, maybe I was calling them, of those rectangles would need to get smaller, right? But that would improve our estimate. Let me show you a picture on the next page to try to explain that. So here is a bunch of right endpoints. Here are a bunch of left endpoints. And this is for the same function, x squared. So you can see the overestimates with fewer rectangles, it's more of an overestimate. As the number of rectangles increases, the air, you can see the air is all this stuff, right? This is all the air. The air begins to minimize as you take more and more. Same thing happens for the left endpoints. So here was our underestimate, the left endpoints, but we have air. These gaps are the air. But as you take more and more rectangles, those gaps begin to be filled and our air gaps lessen, right? And as we do more and more, here's n equals 50. This would be what we see as 50 rectangles. We just used 3. But you can see that that underestimate becomes closer and closer to the true value. Okay. So what should happen, what do you suppose happens when we let n, the number of rectangles, so we're going to call n the number of rectangles that we use. So in our previous one, which I'm not going to show actually, n would have been 3. So what happens when we let that n approach infinity? So in the limit, as n is allowed to approach infinity, in other words, the number of rectangles gets more and more and they go all the way to infinity or approach infinity, then what happens is the exact area appears. So what do you suppose happens when we let the number of rectangles approach infinity? We get the exact area. That's what happens. So here's the definition. The area under a curve of a continuous function f is the limit of approximating rectangles. So here's the limit as n approaches infinity. Again, n is that number of rectangles. R sub n is what we were doing before. That's the rectangles, up to some number of rectangles, n. For us, I had 3. Here is our function value. That's the height of the rectangle. Here is what we're calling delta x. That's the width or the length, as I was calling it, of the rectangle. So on our previous examples, we had v of 0 and like v of 1 and v of 2. That was our function. That was our height of the rectangle. And then we had a bunch of 1s. that I was multiplying by, that's delta x. We're going to use delta x as b minus a over n, the number of rectangles. Just for our example, by the way, we had 0 to 3, just to touch base on it. So I'm talking about this example now. Right, so we had 0 to 3. And if I took, so this would be a and b in terms of this. So I'd have 3 minus 0. And if I use 3 approximating rectangles, right, I'm using 3 for n, and I would have 3 over 3, in other words, 1 for delta x, the width of those intervals. And that's why we had a bunch of 1s repeating. That was just multiplying by 1 every time. Okay, let's try one kind of more formally now with this new notation. So it says estimate the area under the graph of f of x, which is 1 over x, from 1 to 3, using 8 approximating rectangles and right endpoints. So right endpoints. So that makes a difference. Sketch the graph, and the rectangles is your estimate an underestimate or an overestimate. Okay, so I'll start by drawing the graph. So 1 over x, I've split up my scales this way, by the way. So I'm going 0, 1, 2, 3, and then actually just a third, 2/3, and 1. So at 1, we have 1 over 1. Maybe I'll do this in red again. Right? So evaluate this function at 1, and you get 1 over 1 or 1. Evaluate at 2, and you get a half. So I guess a half would be right about here. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4.5. 1, 2, 3, 4. Yeah. So that would look good. And then at 3, we're at a third. Right, plug in a 3, we get 1 over 3. And then I'll do my best to draw this curve. Okay, so there we go. If I'm using 8 approximating rectangles, then that means I would have, let's see, I'll draw this in dark blue. So here's 1, 2, 3, 4, 5, 6, 7, 8. So actually each little square here is going to have its own rectangle. If I'm using right endpoints, then I'm going to the right and going up this way until I hit the curve, and then I go to the left and make a rectangle. I go to the right, go up, and then to the left. So these would be my 8 approximating rectangles. So that's the sketch. Sketch the graph and the rectangles. That's the sketch and the graph. Is your estimate an underestimate or an overestimate? So if we look at it, we would have air here, right? There's a gap there. We would have this missing piece, and these are all under the curve. So this would be an underestimate in this case. So it's not that right endpoints will always be an overestimate. If the function's increasing, then right endpoints are an overestimate in that interval. If a function is decreasing, then the right endpoints are actually an underestimate in that interval. So it depends. Okay, so we still need to estimate the area using these right endpoints. So delta x was stated to be b minus a over n. So in this case, we would have 3 minus 1 over 8. In other words, 2 over 8 or a quarter. That tells me that each of these widths is a quarter, and that should make sense. So we had that the Riemann sum, let me make sure I'm using the right notation. So R sub 8 would be f of x sub 1, the first rectangle in other words, times delta x, which is 1/4, plus f of x sub 2 times delta x, which is still 1/4, plus, I'll go dot 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 since I'm running out of room, we're going to go all the way up to x sub 8. And then times another 1/4. So what I can do is factor out 1/4. So x sub 8 would be equal to 1/4 times f of x sub 1 plus f of x sub 2 all the way to f of x sub 8. Okay. So let's go ahead and start evaluating this. So x sub 1, here's x sub 1, here's x sub 2, 3, 4, 5, 6, 7, 8. All right. So I'll have this equal to 1/4 of f of 1.25, right? That's where this first one is, 1.25. And then I'd have plus f of 1.5, right? That's where this one is, plus f of 1.75, plus f of 2, plus f of 2.25, plus f of 2.5, plus f of 2.75. Running out of room. So plus f of 3. You can see that, sorry. So that would take us to the end. So I just need to find all these. I need to calculate all these things. All right. So what I'll do is I'll grab my calculator. Maybe I'll grab some more paper too, just to help us out. So evaluating our function at these values now, right? So I'll have this equal to 1/4 times 1 over 1.25 plus 1 over 1.5 plus 1 over 1.75 dot 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 all the way to 1 over 3. So I'll go ahead and do this now, and you might want to fast forward, but I'll go ahead and do this now in the calculator. So I'm typing in 1/4, and then I'll have times all these fractions, 1 over 1.25 plus 1 over 5 plus 1 over 7.5, sorry, 1.75. Okay, so I'm going to continue that all the way until I get to 1/3. Okay, so I got about this. Okay, so that was my, just to be clear about what that number is, that's my underestimate of the area under this curve from 1 to 3 using 8 approximating rectangles. So I'll round that to 4 decimal places. It's an estimate after all anyways. So on the calculator it was about 0.9032. Okay, so that was that one, using right endpoints. So let's try it again, and we'll just use the left endpoints. Then we'll go on to another one. So I'll draw this function again. And then for the left endpoints, I'll do these in light blue. So here's the left part of my first interval. So I'm going to go up from there until I hit the function, and then go to the right, and then come down to the next beginning of the interval. Here, go up until I hit the function, go over until I get to the next interval. Here, go up until I hit the function, over. Okay, so here is the picture. Again, we have 1, 2, 3, 4, 5, 6, 7, 8 rectangles, and here are the left endpoints. So this will be an overestimate in this case, right? So again, we'd have delta x as 3 minus 1 over 8. In other words, 2 over 8, or a quarter. And then I would have my Riemann approximating rectangles here. So this R would be these approximating rectangles, sub 8. Again, I can factor out that 1/4, so I'll just go ahead and do that now. And then I'll have f of 1, because that's the first part. That's kind of the function or the number that I evaluate to get the height of this rectangle, right? It goes up from 1. It doesn't really go up from here. That's for our second rectangle. So I'll have f of 1 plus f of 1.25 plus dot 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 plus f of, eventually I'll just get to this rectangle. So the last one is actually from 2.75. Okay, I don't go all the way to 3 this time, because when I make this rectangle, that gets me all the way to 3. So I don't actually start at 3 and go up. I did in the right endpoints case, but not in this case. All right, so now I need to evaluate this. So I need to find f of 1, all these things. Maybe I'll come down here. So 1/4. All right, maybe I can write them all out. Plus f of 1.25 plus f of 1.5 plus okay. So in other words, I would have to plug all these numbers into the function, which is 1 over x. So I'd have 1 over 1 plus 1 over 1.25 plus 1 over 1.5, sorry, just 1.5, plus 1 over 1.75, plus 1/2, plus 1 over 2.25, plus 1 over 2.5, plus 1 over 2.75. So I'm going to type all that in. I can just delete my last one from before. Let me show you what I mean. So I'm just deleting the 1 over 3 part that I had at the end. I'm at least trying to. So there we go. And then I can scroll all the way over here. And I have no idea why it's a block right now. Usually it's a little cursor thing. Anyways, these types of things happen when you're recording videos. So I'll just add in a 1 over here. So 1 plus. So I just squeezed in my 1 over 1 like that, because this one is really the only new one. Press equals. This should be an overestimate now. So I'll round that to 4 decimals again. So this is equal to 1.06, and I'll just say 99. And yeah, if you wanted to, oops, there we go. If you wanted to make a better estimate, you could take the average of these two now. These two, if you get, I can't get those in the same, there we go, these two numbers. Right, so you could take an average of those, but we weren't asked to do that. We were just asked to repeat part 1 using left endpoints. All right. So let's try example 5 on page 90. I know this stuff can be strange at first, so I'm trying to do a good amount of these. It's going to be a longer video for that reason. So estimate the area under the graph of f of x equals x squared plus 1 from -1 to 3 using 4 rectangles and right endpoints. Then improve your estimate by using 8 rectangles. And it says sketch the curve and the approximating rectangles. Okay. So we're going from -1 to 3. We're using right endpoints. We're expected to use 8 rectangles. Sorry, that's the improvement. Use 4 rectangles first. Okay. So I'll go ahead and sketch the curve first. So from -1 to 3. So at -1, evaluate the function at -1 and we get a 2. Evaluate at 0. And we get a 1. Evaluate at 1 and we get a 2. Evaluate at 2 and we get a 5. And then evaluate at 3 and we get a 10. So this is our curve, this piece of this parabola. And it says to use 4 rectangles, so I'll have 1, 2, 3, 4. So if I want to figure out where to go, my A is -1 and my B is 3. So that delta x will be 3 minus -1, and then I'm using 4 rectangles in this case. So I would have delta x is 4 over 4, in other words 1. So I'm going to go 1, 2, 3, 4, like that. Okay. So the approximate area using 4 rectangles, I'll go ahead and factor out that 1. That's delta x. You can always factor that out. So I'll factor that out. And then I'll have f of, let's draw the rectangles actually. So right endpoints, so here's my first interval, and go to the right part of your interval, go up until you hit the function, and then make a rectangle to the left. So go to the right part of your interval. This is for right endpoints. Go up until you hit the function, go over and make your rectangle. Right part of the interval, go up until you hit the function and over. Right part of your interval, go up and over. So this is a bit of a mixture of an underestimate at first, and then it becomes an overestimate because we have this decrease to increase in this interval. So I first evaluate at 0, so this will be f of 0, that first height of that rectangle, f of 1, f of 2, and then f of 3. These are the heights, right? Each of these is a height of a rectangle. This is associated with each of them. That's the width of each of those rectangles. So r sub 4, we'd have 1 times f of 0 is 1, right? 0 squared plus 1, plus 1 squared plus 1, plus 2 squared plus 1, plus 3 squared plus 1, right? These are all the functions. X squared plus 1, x squared plus 1, x squared plus 1, x squared plus 1. So let's see what we get out of that. We have 1 plus 1 plus 1 plus 1, so we have 4, plus 1, 5, plus 4, 9, plus 9, it looks like 18. And I don't know what units those are, so I'll just go units squared for square units. Just making sure I added correctly. So 1, 2, 3. Yeah, I'm happy with that number. Okay. So that was right endpoints, and then it says improve your estimate by using 8 rectangles. So I'll do that down here. So I'll draw the curve again. Okay. So using 8, this is where I'm improving it. So n equals 8 here. So for that reason, delta x will change. It'll still be 3 minus negative 1 because a and b haven't changed, but now n is 8. So I have 4 over 8. In other words, 1/2 is going to be the width of each of these rectangles. I'm still using the right endpoints. So I'll have an interval there, 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 and there. So here's my first interval. You can tell what I'm doing with my pen. I'm just going that far, right? So we go up until we hit the function and over and make a rectangle. Next one, up and over, make a rectangle. Next one, up and over, 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 and then finally up and over. So here are the rectangles in this case. So I'd have r sub 8 would be equal to, now we have 1/2 factored out front. That's the width of all these rectangles, so I'm factoring it out front. And then I have, so for my first one, I'm taking negative 1 and adding 1/2. So that'll be f of negative 1/2 plus f of 0 plus f of 1/2, and so on. All the way up until you get to 3. So f of 3 will be our last one. So just to write it out, maybe I'll come down here so I have more room. So r of 8, sub 8 rather, we'd have 1/2. Our function is x squared plus 1. So I'll have negative 1/2 squared plus 1 plus 0 squared plus 1 plus 1/2 squared plus 1, right? I'm evaluating the function at each one of these right endpoints. Each of these things is a height. Right, so this is the height of the first rectangle here, right here. This is the height of the second rectangle right here. This is the height of the third rectangle right here. The widths of the rectangles are all the same. They're all this 1/2, so I just factored that out. So we would keep going and say, okay, 1 squared plus 1 plus, I'll just switch to decimal, 1.5 squared plus 1 plus 2 squared plus 1 plus 2.5 squared plus 1 plus 3 squared plus 1. So all of that is going to be multiplied by 1/2. I'll enter all that in my calculator now. Okay, so I got 31/2 or 15.5. Check me on that though. So 15.5, and that would be square units, and that is apparently closer to the true value. We got 18 before. That's more of an overestimate than this is, but this is still an estimate. Okay. Guess I forgot to box that. Okay. So let's see, I'm gonna do one more. I'm just deciding which one to do. I'm gonna do on page 93, this one. It says estimate the area under the graph of this function x minus 2 ln x from 1 to 5 using 4 approximating rectangles and taking the sample points to be in part A, you're supposed to do right endpoints. And then part B, we're supposed to do midpoints. So I haven't talked about midpoints yet. So maybe I'll go ahead and do that for this example. So I'm going to skip to part B just so you guys can see some of this stuff. Okay, so it said to use midpoints. It says, I believe, 4 rectangles. Just looking at another copy. Yeah, so it said using 4 approximating rectangles, taking the sample points to be in part B midpoints. So we're going to sketch the curve and the rectangles. Okay, so from 1 to 5. So we're just going from 1 to 5. And what else? So I'll go ahead and evaluate this function. I'll just write the function up here. It's f of x equals x minus 2 ln x. And then we're going from 1 to 5 using n equals 4. Okay. And we're taking midpoints. So let's see, we'll have delta x equals 5 minus 1 over 4. So this is 4 over 4 So these rectangles will have a width of 1 for our information. Let's go ahead and plot the graph of this. So at 1, evaluate this function. Maybe I'll zoom out for you guys. I don't know if that helps a ton. Maybe that helps. So over here at 1, if I evaluate this function there, I'll have 1 minus 2 ln of 1. ln of 1 is 0. So I'll just have a 1 there. So at 1, I get 1. At 2, I'll use my calculator. 2 minus 2 times ln of 2. Just do your best on graphing that. It's about 0.6. So at 2, we're at about 0.6, so 0.2, 0.4, 0.6. At 3, let's see, 3. So we're at 0.8. 3, so a little over 0.8. At 4, some of this stuff is tedious. So about 1 and a quarter, I'll say. Right about there. And then the last one at 5. I'm doing this on my calculator over here. So here's the last one, evaluated at 5. It looks like about 1 3/4. Maybe right about there. So we have this kind of thing happening. Okay, so we will have a width of 1 for our approximating rectangles. And let me zoom back in. So, okay. Here's 1, 2, 3, 4 rectangles. The only thing is, instead of going to the right and drawing up, and then going to the left, or going to the left and drawing up, we're gonna go right in the middle. So x1, kind of the first part, the first piece, we're gonna go right here. That's gonna be 1.5. I'm gonna go up, and then make a rectangle of that height throughout that interval. I'm then gonna find the midpoint of the next interval. I'm gonna go up and then make a rectangle of that height. Hopefully this is making sense. Find the midpoint of the next interval, go up, and make a rectangle of that height. So I'm now using the midpoint to define the height of the rectangle, not the left or the right. The midpoint is kind of like a way of taking the average all in one step. So find the midpoint, go up, and make a rectangle of that height. So here are our 4 approximating rectangles. In other words, I'm taking my x1 to be 1.5, then x2 is 2.5, x3 is 3.5, and then x4 is 4.5. So for my approximating, I'd have r sub 4 as, I'll just write it all together now, this time. So I'll have, I'll just write it in general first. So this would be f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x, and then plus f of x sub 4 times delta x. Okay. So x sub 1 is 1.5 and so on. I can factor out delta x. So r sub 4 will be delta x. And then just f of x sub 1, x sub 2, x sub 3, x sub 4. So now actually evaluating these and plugging in delta x, which we know to be 1. So I'm going to plug in 1.5 into our function, this function here. Okay. And I'll probably just estimate again, maybe round to 4 decimal places again or something like that. So this will be 1 times f of x sub 1 means take 1.5 and plug it in. So I'll have 1.5 minus 2 times ln of 1.5 plus 2.5 minus 2 times ln of 2.5 plus 3.5 minus 2 times ln of 3.5. And then finally plus 4.5 minus 2 times ln of 4.5. Okay, so I'll type all this stuff into my calculator now and just round. So to 4 decimal places, I got this number here. Okay, so this would be about equal to 3.8428, and that would be some unit squared. Okay, on to 5.2. This is where the magic happens, kind of where we're going to be able to find these values exactly. There's not going to be any more approximating. We're going to use the mechanics of a limit to take our approximates to an exact place. Okay, so we have, here's our definite integral kind of notation. Integral, antiderivative, kind of the two pillars. One of the two pillars of Calc 1, as I've been saying. Here we have the integral sign. So this means you're integrating from the upper and lower limits. So we'd have the lower limit as a, the upper limit as b. So this would be saying, hey, I'm integrating from this interval starting at a to b of this function f. And this dx is, for now, we'll just call it a tiny slice of the x-axis. And that's really defining the variable of integration. So that's going to work as like a tiny width rectangle, basically. So what this process is going to allow is that instead of getting all these rectangles and then having this error, we're eventually going to exactly fill out this area by the use of a limit. So here's the main rub right here. So we have been doing, in the previous section, we've been doing this actually. I haven't used the sum notation yet, but we're about to use a lot of that. Then what we're going to do within that sum is we're going to evaluate a limit of that sum. And when we do that, in the limiting case where n approaches infinity, in other words, the number of rectangles approaches infinity, then you do indeed get the exact area under the curve, and that's what this set of symbols represents. This is our exact area under the curve. Okay, so let's start with this next page. So page 97 kind of gives us the layout, kind of defines some of the terms. So we have the same delta x, b minus a over n. We're able to locate all these x sub i's this way. So we'll take the beginning of our interval and then add some I times delta x there. And that'll be the main couple things that we use. When it comes time to evaluate sums, we'll do so using these three replacements. So whenever we have something like this, we can replace it with this. Whenever I have something like this, I can replace it with this. Whenever I have something like this, I can replace it with this. Just to remind you, the sum on I, so if you have the sum on I going from 1 to n, that would be 1 plus 2 plus 3 plus 4 plus dot 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 n. And what this is the result up to sum n. So if n is 2, I would have 1 plus 2 is 3. And if you plug in 2 here, you have 2 times 3 over 2. Here's a 3 also. So this is just tracking the sum up to some letter n. This is tracking the sum up to some letter n. There are a few sum rules that we'll be leveraging also. So yeah, the next couple problems will be a challenge as far as how to calculate sums. So I'll do at least 2 problems, but I realize this video is quite long at this point. All right. So this example 1 says evaluate the Riemann sum for this by taking sample points to be right endpoints, and a of 0, b is 3, and n is 6. So this will be an approximate. So this is our approx. And then down here it says evaluate. So this is where we'll attach a limit to this, and this will be exact. Okay. So up here we're going to do this similar to the previous section. So the Riemann sum in its full glory, I'll try to use the same notation. What is meant by Riemann sum is this sum. So we're going from I equals 1 to some number of rectangles. In this case, it'll be 6. And then we have f of x sub I, in other words, the height of each individual rectangle. Sorry about that. This is what I was writing. So I have the Riemann sum as the sum from I equals 1 to n of f of x sub I times delta x, the width of each rectangle, right? This sum just means we're adding each of those up. So defining some of the things with respect to our particular case. So delta x would be 3 minus 0 over 6. So delta x will be 1/2. To figure out these, the x sub i's, it was given that x sub I will be a plus I times delta x. That was on that previous page. So for these 6 rectangles, I can define x sub I, let me rewrite that, x sub 1 as 0 plus 1, right? If I is 1 there, then I is 1 here, times 1/2. So x sub 1 is 0 plus 1 times 1/2, in other words, 1/2. This is the x location that defines our first rectangle's endpoint. So here's a picture of it. So basically, this would be 1, This would be 2, and here's 3. So here's our first one. That's why we're getting a half for x sub 1. X sub 2 would be 0 plus 2 times a half. In other words, 1. X sub 3 would be 0 plus 3 times a half, or 3 halves. X sub 4 would be 0 plus 4 times a half. So that would be 2. Maybe I'll highlight these. So we're looking at this, 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 this. X sub 5, 0 plus 5 times a half. In other words, 5 halves. And then x sub 6 is going to be our last one, since we're stopping at n equals 6. So x sub 6 is 0 plus 6 times a half. In other words, 3. Okay. So let's go ahead and go about this now. So the sum, we'll have the sum going from I equals 1 to 6 of f of x sub I times delta x. So in other words, that sum would be f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x plus dot 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 all the way up to f of x sub 6 times delta x. Right, that's what the sum means, is cycle through I equals 1 to 6, right, just operating on this I right here. So here's I equal to 1, here's I equal to 2, I equal to 3. So this is the sum. And I do know that x sub 1 is 1/2, x sub 2 is 1, and so on. So this would be equal to f of 1/2 times 1/2, right? Because delta x is also 1/2, plus f of x sub 2, which is 1, times 1/2. X sub 3 is 3 halves, so I'd have plus f of 3 halves times 1/2. Plus dot 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 all the way up to the 6. I'm just writing it this way because I'm running out of room. So I'd have f of 3 times 1/2. Okay? So going ahead and typing that in, what I'm now going to do, and it's going to take a little bit of time, I'm now going to take 1/2 and plug it into the function to see what the height of the rectangle is there. Right? So right here, just to continue this so you can see a bit of what I'm doing, I'm taking 1/2, plugging it in. Maybe I'll factor out the half from everybody also. So f of 1/2 means take 1/2, cube it, and then minus 6 times 1/2. Right, that's what our function is saying to do. That's how we get the heights. So that's the first height, and then plus 1 cubed minus 6 times 1 plus 3 halves cubed minus 6 times 3 halves plus dot dot dot. I'm just skipping some. Not that I'm mathematically skipping them, I'm just notationally skipping them because I'm running out of room. And then I'll have 3 cubed minus 6 times 3 as my last one. So I'm going to go ahead and type those in now and then write down that estimate. Okay. So I'll have 1/2 out front times 25 cubed plus plus 27 plus almost there. And plugging in 3 cubed plus 3 cubed 6 times 3. So I may have made a mistake, but you guys can check me on this. I'm getting negative 63/16. I'll write this up here. So this would be about equal to this area. In other words, I'm liking the negative number because we have more area below. The area that's counted below the x-axis would be counted as negative area, actually. So this is negative 3.9375, and that would be some number of square units. Okay. So let's go down here and try this exactly now. Okay, so on to part 2. So to evaluate this integral, we actually need to evaluate a limit of this Riemann sum. So this exact integral will equal the limit as n approaches infinity of a sum. We know that delta x is 3 minus 0, typically over n, where n is some finite number. But here we're going to need that n approaches infinity. So delta x for us is just going to be 3 over n. Okay. X sub I in general is a plus I delta x. So we'll have 0 plus I times delta x, which is 3 over n. In other words, x sub I for us is 3 over n I. Okay, so we have delta x as 3 over n. We have x sub I as, in this case, 3 over n times I. So now we're going to plug both of those things in here, and then eventually plug those things into the function. So the limit as n goes to infinity of this function, going from 1 to n, we'll have f of x sub I, f of 3 over ni, times delta x in our case is 3 over n. Okay? So 3 over n does not depend on I. The only thing that needs to stay in the sum is anything that involves I. So since 3 over n does not involve I, it can come out of the sum, but it does involve n, so it'll need to stay inside of the limit. So this would equal the limit as n goes to infinity of 3 over n times the sum I going from 1 to n, and then actually plugging this into the function, right? Our function is x cubed minus 6x, so we would have 3 over n I cubed minus 6 times 3 over n I. So all of that is in the sum. Okay, so I can go ahead and cube now. So cubing these things, it's a lot to write, I realize. So take your time. So we still have 3 over n. And now actually cubing 3ni, I'll get the sum, I goes from 1 to n, of 27, so I'll have 27 over n cubed times I cubed, right, if I cube this. And then also in the sum is this stuff here, so I'll have minus 18 over n times I. Okay. One of the properties that is on page 97, specifically number 11 on page 97, is that the sum of a difference is the difference of sums. So I'm going to use that. Grab a new sheet of paper, actually. So what I'll do is I'll split this into 2 sums. So this would be equivalent to the limit as n goes to infinity. That's an infinity symbol, believe it or not, of 3 over n. And then I'll have braces, the sum from 1 to n, 27 over n cubed I cubed, minus the sum, I goes from 1 to n, of 18 over n I. Similarly to the 3 over n, 27 over n cubed does not depend on I, nor does 18 over n. So I can bring this out front of the sum and this out in front of the sum. So we have the limit as n goes to infinity of 3 over n, and then times 27 over n cubed times the sum goes from I equals 1 to n of I cubed minus, I'll bring out the 18 over n as well, and then sum going from 1 to n of just I. A lot of weird symbols going on. So this and this. So focus now on this and this. So on also page 97, you'll see there are formulas for the sum of I and the sum of I cubed. There's also one for the sum of I squared, which isn't popping up here. Just the cube and the I are popping up. So we'll use on page 97 numbers 5 and 7. So I can replace the sum of I cubed with n times n plus 1 over 2 all squared. So this is equivalent to the limit as n goes to infinity, 3 over n times 27 over n cubed times n plus 1 all over 2 and then squared. That's for the cube. Again, that's page 97 and that's number 7. Here I can replace the sum on I, so I'll still have minus 18 over n, but then times number 5 on page 97 says n times n plus 1 over 2. We still have all that in the limit. Okay. So simplifying, eventually we're going to evaluate the limit. So I'll simplify a bit. So this is the limit, n goes to infinity, 3 over n. And then let's see, we have 27 over n cubed times n squared times n plus 1 squared over 4 minus, it looks like I can cancel the 2, so I'll just say minus 9, and I'll cancel an n as well. So minus 9 times n plus 1. And so I kind of canceled the 2 with an 18, goes 9 times, canceled the n. But we can do more canceling, I realize. Okay, so maybe I'll do a little bit more canceling over here. So n squared can cancel with the n squared there. And let's see if I can write something more simple down. So limit n goes to infinity of 3 over n, and this is multiplying back in, and I'll have a 27 over 4n times n plus 1 all squared. Minus n, 9n minus 9. Sorry, that should just be a parentheses. And now I can maybe go ahead and multiply back in this n here. This 3 over n, rather. Okay, so multiplying that back in, we have the limit as n goes to infinity. 3 times 27 is 81. And then I'll have over 4n squared. And then I'll maybe actually factor that up there. So we have 81 over 4n squared times n squared plus 2n plus 1. Right, that was bringing in both the 3 and the n. So that's why I got an n squared and an 81. And then also distributing the 3 over n over here. So I'll get minus 27, and then the n's actually cancel. Right, the n's actually cancel there. So I'll just have minus 27 and then minus 27 over n. So I'm taking the limit of all this stuff. Okay, so the limit of all this sum and difference, I can basically pass through the limit. So I can say limit as n goes to infinity. Sorry if you couldn't see that. Of, I'll say 81n squared plus 162n plus 81 all over 4n squared. That'll be my first limit. And then minus limit as n goes to infinity of 27, right? This one, I have the minus out front. And then minus limit as n goes to infinity of 27 over n. So we can evaluate these limits now. I don't know why it just got darker. Okay, we'll see what happens. So the limit as n goes to infinity, well, we're allowed to divide everything by the largest agreed term in the denominator, which would be n squared. But basically, it'll be the ratio of the leading coefficients that we're left with. So this would be equal to 81 over 4. The limit of n approaching infinity of 27 just is negative 27. And then this is 0. As n goes to infinity, this will be 0. So 81 fourths minus 27 is our answer. So it looks like negative 6.75. And this would be some square unit. All right, talk to you soon.